job in the line of the world scientist community. A couple of researchers in the Northeast showed their expertise and excellence
Yes, sir.
in this area in the recent years. That is a proud moment for us.
Okay, okay.
Personally, I feel as the Northeast sky is quite clear and comparatively free from airborne pollutions, it may give the opportunity to carry out experimental research apart from those analytical theoretical approaches. Department has a good research group led by Dr. Sanjit Singh, assistant professor in this area, and they have constantly working on their projects. I welcome all of you for joining this auspicious event of 7th Northeast Meet of Astronomers on behalf of the Department of Physics, especially Professor Samox Raisudhari and Professor Ajit Kambai from IUCAA, who have promptly accepted our invitations for these inauguration functions. Thank you, sir, for your kind presence. I also welcome and grateful to our Honorable Vice Chancellor, Professor Sakit Kushwaha, for his valuable suggestion and assistance in holding these events. Thank to Professor Professor Amitav Mitra, Registrar,
सागर भैया नेट को क्या हो गया
from today, 27 to 29th January, through online platform because of again sudden charge of COVID-19 pandemic. The event was initially it was planned as offline in the department, but the situation again compelled us to make it online. A good number of papers has been accepted for a presentation in the workshops, and I hope there will be good interactions among the participants and research persons. The participants would get the opportunity to carry forward their ongoing research with the directions, suggestions, and expertise from the learned research persons. I do believe that their lecture will enlighten their audience with the expertise in this field and motivate the researchers and the students. At the end, I would also like to thank our Honorable VC, Pro VC, Registrar, all deans of faculties, HODs, the research scholars, students, and participants for joining us in this event in the online platform and hope for make it a grand success. I would also like to special thank to Dr. Sanjit Singh for his team for coordinating and supervising all the works for this workshop. I also would like to appreciate the assistance from the non-teaching staff and MSc students and lot of thanks to them. Thank you all.
Thank you very much, sir. Now, I would like to request our Dean, Faculty of Basic Science, Rajiv Gandhi University, Professor Sanjeev Kumar sir, to kindly say a few words on this auspicious occasion.
Thank you, Navu. A very good morning to all of you. Honorable Vice Chancellor, Rajiv Gandhi University, Professor Sakit Kushwaha, respected Professor, Pro Vice Chancellor, Professor Mitra, our Registrar, Dr. N.T. Rikam, today's special guest, Professor Somek Rai Chaudhary, Director IUCAA, my fellow colleagues, participants, ladies and gentlemen. At the onset, I would like to welcome to all of you on the behalf of the Faculty of Basic Science in the capacity of the Dean of the Basic Science of Rajiv Gandhi University to 7th Northeast Meet of the Astronomer, also abbreviated as the NEMA. Astronomy seeks to explain everything we observe in the universe, from the comets, planets, and stars in our solar system to distant galaxies to the echoes of the Big Bang. Physicists study the cosmos to understand how the physics works at conditions that are not possible to create in Earth, to get an idea of where we come from and where we are going. What is the fate of our universe and its unique, it is the existence and many more. Although it is always being a debated topic that whether investing large sum of the money in these researches in a good idea of people cannot directly see the benefit they will get from the outcome, and it is true that researchers like this rarely contributed directly with the tangible outcome on a short time scale. But it is also true that pursuit of this research required cutting edge of the technology and method that on a long time scales can make a difference through their broader applications. There are many examples of this, such as the film known as the Kodak Technical Pen, was originally developed to record the changes in the surface structure of sun, but is now vastly used by the medical and industrial spectroscopists, industrial photographers, and artists. The charge-coupled devices was first used as a sensor for imaging the capture of the astronomical images, but very shortly found their place in camera, webcams, and mobile phones also. Other examples are communication satellites, solar panels, GPS, and MRI scanners also. So we could see that the study and understanding the cosmos not only help to improve the existing concept of science, but also adds to betterment in the quality of living. Lastly, I would like to congratulate and thanks to Dr. H.S. Singh and Dr. Rajiv Misra for organizing this three-day event in our university and wish this program to be a huge success. Thank you very much.
Thank you very much, sir. Now, I would like to request our respected registrar, Dr. N.T. Rikam, sir, to kindly say a few words. रजिस्ट्रार नहीं बोल रहे है ना है रजिस्ट्रार है सागर भैया रजिस्ट्रार नहीं बोल रहे हम बुला तो दिया रजिस्ट्रार को नहीं बोल रहे लेकिन ये क्या Now, I would like to request our respected registrar, Dr. N.T. Rikam, sir, to kindly say a few words.
Please check if there's any problem over there, connectivity issue.
There is no connectivity issue in this site, so we would like to proceed next. Now, I would like to request our Honorable Pro Vice Chancellor, Professor Amitwa Mitra, to kindly share a few words with us.
Good morning and namaste to all of you. Professor Saket Kushwa, Honorable Vice Chancellor of Rajiv Gandhi University. Our special guest, Professor Somak Raichaudhuri, Director, IUCAA, Pune. Dr. N.T. Rikam, Registrar, Rajiv Gandhi University. Professor Sanjeev Kumar, Dean, Faculty of Basic Sciences. Professor Pradeep Kalita, Head, Department of Physics, Rajiv Gandhi University. Eminent resource persons, delegates from various states of Northeast India, faculty members, research scholars, ladies and gentlemen present. At the very outset, I would like to congratulate Department of Physics, Rajiv Gandhi University for organizing Northeast Meet of Astronomers in association with Department of Physics, Tezpur University, and Inter-University Center for Astronomy and Astrophysics, Pune. Well, if we go through in fact, astronomy is the oldest of the natural sciences. If we go through the history of mankind, we always find that human beings have always looked into the sky to navigate the vast oceans, to decide when to plant their crops, and to answer questions of where we came from and how we got there. It is a discipline that opens our eyes, gives context to our place in the universe, and can reshape how we can see the world. When Copernicus claimed that Earth was not the center of the universe, it triggered a revolution through which religion, science, and society had to adapt to this new world view. In fact, thus astronomy has and continues to revolutionize our thinking in a worldwide scale. Since it is one of the oldest sciences, it is a part of every nation's culture, history, and roots. If we come to our state in Arunachal Pradesh, we find that Doinipolo, that is the sun and moon, is the epicenter of the culture of the multi-tribes of Arunachal Pradesh. Well, physics is closely connected to astronomy. Physics is used in the design of instruments, the interpretation of the data, the instruments produced, and finally, construction of the grand theories which explain the evolution of stars, galaxies, and universe. If we come to India, we find that astronomy is well known, that the period during about several centuries from Aryabhatta to Bhaskaracharya was the golden age of Indian astronomy. Even nowadays, the Indian astrophysics are making a path-breaking research on various fields of astrophysics. It is now time for Northeast Indian scientists and astrophysicists to enhance knowledge and capability in the field of astrophysics, and there is a great scope for it. I hope that NEMA, Northeast Meet of Astronomers, will be able to achieve this goal. My best wishes to the organizers as well as the participants. Thank you very much. Namaste to all of you.
Thank you very much, sir. We are sorry to announce that our registrar, sir, due to technical issue, could not attend the program today. Sorry for the inconvenience caused. Now, proceeding to the next, I would like to request our very special guest, Professor Somak Rai Chaudhary, sir, Director of IUCAA, Pune, to kindly deliver his speech.
Namaskar. Good morning. Thank you very much, everybody, for coming. I'm very happy to be here with the Vice Chancellor, Dr. Saket Kushwaha, and the Pro VC Registrar, Head of Physics. I have to congratulate Dr. Hasnain Shanjit Singh and his group of organizers for organizing this meeting. On behalf of the Inter-University Center for Astronomy and Astrophysics, IUCAA in Pune, we help to organize this Northeastern Meet every year. This is the 7th edition, and I'm so happy to be here with you, but I'm also quite unhappy that I could not be there in person. These meetings always bring together the astronomy resource people from the Northeastern states together, and it's a pleasure being there, meeting everybody. Dr. Mitra just said that astronomy is one of the oldest sciences. It is absolutely true, but I would also argue at the same time, very strangely, it is one of the youngest sciences as well. And that is because even though people wondered about the skies and heavens from the very beginning, because in the absence of television, the skies were the main entertainment for people to look at the sky and try to study the sky and wonder about the universe. It is only recently that we have been able to unravel the mysteries of the universe because of facilities that have come to us in the form of telescopes and detectors and various things that help us actually study the universe. It is less than 100 years that we know that the universe is 14 billion years old, and that we live in a galaxy. Even Einstein, when he published his theory of relativity in 1915, did not know that we live in a galaxy, and the stars are in galaxies, and the universe is so large. So this comes to us because physics has entered astronomy. Astrophysics is far, far more than studying the stars in the sky. It is about applying the laws of science that we know, physics, chemistry, biology, that we see in our lives onto the universe. I would invite you to understand that this is a huge leap of faith. Even until a few hundred years ago, people did not think that the same laws of science apply to us as to the heavens. And the fact that we can study a star or a galaxy or even the universe using Newton's laws of physics or Einstein's laws of physics or our mathematics is itself a big triumph. And with the advent of the space era, we can now put telescopes in space and open up the whole electromagnetic spectrum for us, instead of only observing the universe through our eyes and the light that our eyes can see. We now use radio telescopes, X-ray telescopes, gamma ray telescopes, UV telescopes, radio telescopes, microwave telescopes, millimeter wave telescopes. In the last 5 years, we've been using gravitational wave telescopes. That opens up a parallel way of studying the universe, not even involving electromagnetic radiation. From space, from the Earth, there is no boundary anymore. So it is very rare that we live as practitioners in a science that is rapidly expanding and is just becoming a new subject of its own. The revolution in astrophysics now is the same as what happened to basic physics at the beginning of the 20th century, when the atom was, people looked inside the atom, started discovering the particles, the electron, the proton, and the neutron, and quantum mechanics was invented, and the entire subject of physics changed. Astrophysics is changing like that now. And more importantly, unlike what happened in physics or chemistry at that time, 100 years ago, in this particular subject that's opening up, India is playing a very, very important role. Indian facilities are becoming very important. We have facilities dotted across the Himalayas, from Ladakh to the northeast. We have radio telescopes. The biggest radio array in the world at low frequencies is in India. And we are getting into this mega project of the 30-meter telescope, the square kilometer array, and the gravitational wave observatory LIGO. And this is why people who are young and coming into the subject now have these amazing opportunities. The Northeast region will play a very, very important role in India's role in science right now. You can see this in these 3 days. You can see how much engagement there is from the Northeast in astronomy, astrophysics. And so I would like us to celebrate this and celebrate the fact that India is playing an important role in world astrophysics right now. And this just highlights the importance of meetings such as this. Thank you very much for organizing this. Thank you very much for being here. And I am very, very happy to be part of this wonderful program. Thank you very much. Namaste.
Thank you very much, sir. Thank you very much. Now, I would like to welcome our respected registrar, Dr. N.T. Rekam, sir, to kindly say a few words.
Okay, very good morning to all of you. Am I audible?
Yes, sir.
Yeah. Okay. At the very outset, I must seek apology because of technical fault. I could not join the program on time. But having said this, at the very outset, I greet our Honorable Vice Chancellor, Professor Saket Kuswaha, who is gracing the occasion as chief guest, and of course our Pro Vice Chancellor, Professor Amit Mitra, who has just spoken. Then my greetings to Professor Somak Rai Chaudhary, who is joining us all the way from Pune and has spoken very very brief but very qualitative speech on the topic. The organizers, including Dean of Basic Sciences, Professor Sanjeev Kumar, and all other members who are organizing this program, and of course the collaborators, Department of Physics, Tezpur University, and also IUCAA, Pune, and all the participants. I join the organizers in extending my warm welcome to all of you on this seventh series of Northeast Meet of Astronomers being held here, Rajiv Gandhi University, in collaboration of Tezpur University and IUCAA Pune. I think astronomy is such, it's not new to all of us, but here in this part of the country, this subject, this actually area has not been popularized, has not been actually dealt as much as the other areas we have been actually doing. So this is why it's actually we can say maybe because of ignorance, because of lack of actually having knowledge about the importance of astronomy, we could not able to actually acquaint with this area. But this type of meet, actually, astronomers meets, it will certainly expand the horizon of the area, horizon of astronomy in this part of the country. India is a geographically very large country. Northeast is, I suppose, one of the underdeveloped area in our country. So I hope the scholars, the researchers, and the resource person, they will actually enlighten the participants, and participants will definitely get benefit out of these 3 days workshop or 3 days conference of Northeast Meet of Astronomers. So I extend my best wishes to all of you, especially the organizers. And I suppose this is the first, maybe first time that RU is associating with organizing the meet, and hope in near future will continue to do, and whatever help and support we can actually provide, we will be providing all through. With this, I once again extend my best wishes to all of you. Thank you very much. Thank you.
Thank you very much, sir. Now, I would like to request our chief guest, Professor Saket Kuswaha, Honorable Vice Chancellor of Rajiv Gandhi University, to kindly share few words with us.
Thank you, the Master of Ceremony. Thank you, Madam. I think you are my student. My greetings to Professor Amita Mitra ji, Honorable Pro Vice Chancellor of this university. Warm greetings to Dr. N.T. Rikam, the Registrar of this university, Professor Otam Padung, the Finance Officer of this university, the Control of Examination, Dr. Rajiv, the Dean of Basic Sciences, Professor Sanjeev Kumar ji, the head of the department, Dr. Professor Kolita, and of course, we have the director of the program, Dr. Singh, who took a lot of pain. I think, if I'm not wrong, he was detected or he was found COVID positive. Still, he's doing the program. So, my kudos to him. You see, I'm lucky. When I said FO and then FO is here. So that means if in case of any expenditure, FO is going to give you money. Okay, fine. So now let me go back to my talk, but let me adjust my camera. Yes, okay. So then the speaker of the program today, I think special guest, Professor Samyak Rai Chaudhary Sahab, the director of Inter-University Center for Astronomy and Astrophysics, Pune. Then other partners we have here, I think the Inter-University Center for Astronomy and Astrophysics, Pune is also partner, and Tezpur University. I'm really happy. You see, I do agree that we are suffering a lot because of this COVID issue. And yes, Professor Rai Chaudhary, you are right. These kind of meetings are supposed to be in person. See, interaction becomes more beautiful, more meaningful when we have a physical interaction. We see the expressions face to face talk. So there's nothing better than that. But then Raj Kapoor said in the movie that a show must go on. We should not stop, COVID or no COVID. So we should continue. Life must continue. So when Dr. Singh came to me, he was very worried that, sir, they have agreed to fund the conference. I said, the schedule of the conference will not change. We will not take any money, but we will continue the program online whenever there is because this is 7th chapter. So we are going to have 7.1 chapter, and it will still be done by Rajiv Gandhi University. I mean, ideally, it is supposed to be 8th chapter, and other university will do it. Since we have not done physically, so it will be 7.1 chapter, we will do it here. So with these words, let me welcome the delegates and other resource persons, the chairman of various sessions. You see, let me tell you, I do agree with both previous speaker, Professor Amita Mitra and Professor Rai Chaudhary. You see, about 6-7 centuries ago, people believed that orders used to come from heaven, that means from sky. At that time, there was a lot of science discussing these kind of issues. But in the latter phase, human beings thought that they are supposed to issue the orders also, we are doing that way. So but in India, I believe, when you see the creation, structural creation of how I mean, a lot of observatories are there in India, in Jaipur, in Varanasi also we have. That means people were interested in this science, but then somehow it was misconceived. Like astrophysics, astronomy was limited to chemistry only in India. But I believe that with the new dimension, and then let me tell you other thing also. Those issues, when you don't know much, then it becomes mysterious. To me, sky and looking at the planets and all these things are still a mysterious science. You see, and I believe, like yesterday, I was I think reading Harari's this novel, write-up, Sapien and all these things. There he mentioned that somehow I perceived from those write-ups that when we don't know much, then we don't want to work on it. Whenever those things, some things becomes very popular, like all the other principle of physics and other things, when things are well researched, well documented, well circulated, then interest of people becoming too much in that. But then those areas where we don't have much literature, much avenues, when I said avenues, I should not be misunderstood. That means like when we are applying for the grant, a grant is given to the labs where we can even put the detailed description of the machines. But when I told Singh Saab and even Sanjeev to buy a telescope and install it on the roof of physics department, they did not do it. So see, interest has to be there. I'm not complaining. Dr. Sanjeev, Professor Kolita, and Dr. Singh must not take as my complaint. But what I'm saying is that there's a need for us to actually give somehow equal emphasis to all branches where research could be done. So I believe that this particular seminar is going to throw some light on it. And I would love to have a small laboratory on astrophysics with the help of Inter-University Center for Astronomy and Astrophysics with the help of Director Saab, Professor Rai Chaudhary Saab. Please guide us. Fund will not be problem because FO Saab is here and he's saying, he's nodding his head, money will not be problem. But let us give justice to each and every aspect, because I believe whether you have information or you don't have information, but every aspect, every component of every discipline is very important. So I believe with these words, I'm expecting a good position paper and good policy paper for the micro level, for the immediate creation of a lab, and maybe at the later stage, we could go for further research. And I request the Dean of Basic Science, the head of the department, as well as Dr. Singh, to put up a good proposal which could be funded internally here. And we can also apply with the help of Inter-University Center for Astronomy and Astrophysics. We could apply to DST or other funding agency. Thank you very much. Once again, my greetings to all of you. Jai Arunachal, Jai Bharat.
Thank you very much, Honorable Vice Chancellor, for your kind and valuable words. Lastly, I would like to request Mr. Rajesh Prasad, sir, to kindly deliver the vote of thanks.
Thank you, Mayu. Taking the opportunity of this inaugural session, I, on behalf of organizing committee of this 7th edition of NEMA, would like to convey my heartfelt gratitude and thankfulness to Honorable Vice Chancellor, sir, for being with us despite of his busy schedule. Thank you, sir. Further, my thanks goes to Pro Vice Chancellor, sir, Registrar, sir, FO, sir. My special thanks goes to Director IUCAA Pune. I would also like to thank Dean of Basic Science, Head of Department of Physics, Dean of various departments, Head of various departments, Professor, Assistant Professor, Associate Professor, Speakers, Official and Officers of Rajiv Gandhi University. Further, I would like to thank the participants as well as the research scholars of this department and the MSc students. Last but not the least, I would like to thank Mr. Sagar Singh Gwari, Mr. Sarvan Kumar, Tamiachi Sijingla Sapolo, and Mr. Ringsar Vagari and Ms. Tai Mayu for their support and effort for making this event a successful one. Lastly, I would like to thank each and everyone for their effort for making this program a successful one. Thank you very much.
Before winding up the program, I would like to call our Dr. Sanjit sir to kindly say a few words.
Thank you, Mayu, for giving me these opportunities again. So, thank you everyone for being with us in this inaugural programs of NEMA-VII edition. So, with this, the inaugural sessions concludes here. So, in the continuation of this NEMA-VII edition, so we'll shift to the next technical sessions. Thank you all. Thank you all.
Again. लीव कर देगा ऐसे कहाँ गया नथिंग सर मैं आपको छोड़ के
it's almost 10 to 50. So I think hopefully we have concluded our inaugural programs successfully. So it is supposed to start our technical sessions from the 11th. So among us, I think we have Dr. Biplab Sakar. So
Yes, hello.
I call upon the Dr. Biplab Sakar to take today's first the technical sessions. So over to Dr. Biplab Sarkar.
Yeah, good morning to everyone, and I welcome you to the first scientific session of day 1 of the 7th edition of NEMA. So, in this first scientific session, there are two talks lined up for you. Each of the talk will be of 45 minutes duration, and we will devote around 38 to 40 minutes for the talk, and the last 5 or 7 minutes will take up questions from the audience. Okay. So the first talk will be delivered by Professor Ajit K. Kembabi from IUCAA Pune, and the title of his talk is Our Galaxy and the Supermassive Black Hole at its Center. So I request Professor Kembabi to kindly begin his talk.
Good morning. I'll begin my talk in just a couple of minutes if you give me. I'll be back soon.
Sure, sir.
Can I just share my screen, please?
Yeah, so you can share your screen.
Yeah. Can you see my screen now?
Yes, sir, it's visible.
Okay, all right. So thank you very much, and good morning. I'm very happy to be speaking at this meeting of NEMA. My great regret is that we are not face to face. I would imagine that over the last 25 years or more, I've been going to the east or the northeast of the country at least a couple of times a year. And they have uniformly been very great experiences for me. First of all, because of the beauty of the place, and then the friendship and the warmth of the people there, and also the great interest in science that I've always felt, whether I'm in parts of the Northeast. I have very good friends there, and then I've interacted with many, many students. Unfortunately, that has not been possible over the last couple of years, and I'm really looking forward to when this can begin. So, in fact, I've told my colleague from IUCAA, Rajiv Mishra, who is always at the forefront in these organizations, that I'll accept an invitation to give a talk on video, providing I'm again invited when things become better. I hope that situation comes in sooner than later. Until then, of course, we have to do whatever we have to do. So my talk today is going to be on the Milky Way galaxy and its supermassive black hole. Now, I was asked to talk on galaxies, but you know that it's not really possible to talk interestingly about galaxies in 45 minutes. So I thought that I'll focus on one region of the galaxy, which is the absolute center of the galaxy. And we all know that galaxy centers are very active, and our center is not really very active. And nevertheless, we believe that there is a supermassive black hole. So I want to first review the structure of a galaxy, number one, and then let's see how the supermassive black hole has been discovered. And along the way, I'll also tell you that as you all know already, that half the Nobel Prize for 2020 was given for this particular discovery made quite independently by two groups, one working in Germany and the other in the United States. So I'm sure all of you are familiar with the concept of galaxies, but again there'll be younger students who may not know very much. So a galaxy is like our own galaxy, the Milky Way, is generally a collection of stars, about 10 to the 11 stars. It has got a mass of about 10 to the 11 solar masses, simply because the average star in the galaxy has a mass close to the mass of the Sun. The galaxy contains stars, gas, and dust, and as we know now, a black hole. And much of the mass in the galaxy is in the form of dark matter, whose nature we do not know. And a small fraction of galaxies, like a few percent, are active. Okay, meaning that the galaxies emit very copious form energy, which is not ascribed to the energy produced by the stars acting in division. There is some other source of energy, and when this happens, the galaxy is called as an active galaxy, and in the most extreme cases, as a quasar. So our own Milky Way galaxy, and one of the things I miss, I'm not going to the northeast, is the clear skies, the night skies, when one can actually see stars beautifully. From my own, I live in a rather secluded part of Pune, and the hills surrounding it, and but the problem is that there are a lot of trees and a lot of buildings. And so from where I see, from my terrace, I can see about 4 stars on a good day. Whereas there should be 4,000 stars visible to the naked eye, which is really the bane of large cities now. I remember I was once on the campus of Tezpur University and stayed in a guest house. And at about 6 o'clock in the evening, every day when it was already dark, the lights used to suddenly go off. And the first thing which happened was that all the foxes on the campus used to start shouting loudly. It was quite an experience. And then, of course, the stars popped out, and it was a very beautiful thing that you could see. So if you are fortunate enough to be in a place like that, which all of you are, and I am not, then you can actually see the Milky Way. I remember when I was growing up in North Karnataka, I actually used to see the Milky Way every day, like a band going across the sky. And if you can get a view to the constellation of Sagittarius, which you were not from the northeast, okay, then you can see actually the bulge of the galaxy becoming larger there, particularly on clear nights. Right, so this is just a patch of the galaxy that you are seeing, and here is a Spitzer from the Spitzer spacecraft near infrared image of the central 900 light years. But here is a panoramic view of the galaxy. So you may ask, how do you get a view like this? Since we are by definition living inside our own galaxy. So you do that by pointing. When you look at the belt of the Milky Way, you point your camera to different parts of the Milky Way and take an image, and then you make a composite. But how is this image taken? So there's a Kobe satellite which made great discoveries regarding the cosmic microwave background. And so they had a near infrared image camera which took images of the galaxy at 1.25, 2.2, and 3.5 micron. The near infrared band is going to be very important for us today, as I will explain to you. And then, so you can see the whole galaxy. This is not the whole galaxy; it actually stretches beyond the edges that you see, and you see a thin disc-like structure, and in the central region, you see what is known as a bulge. And the brown parts, again, which will be important to us today, are what are known as dust grains. So the galaxy contains a lot of dust. The dust absorbs light, blue light, and so you see the dust having a red appearance. So so what we are seeing here is the edge-on image of the galaxy. But then if we could come out of a galaxy, go and then take a face-on view of the galaxy, and then this is what you would see. Right, so here the disk actually, there is a large disk which is present, but there are also these spiral arms. We obviously cannot see the spiral arms in our own galaxy directly, but one can see spiral arms in other galaxies. And all of you would have definitely seen images of galaxies, including the Andromeda Nebula, where the spiral arms are obvious. Okay, so now this is not a real image. It's a composite. It's a sort of synthetic image. And then you can see that the spiral arms, they go round and round the galaxy, and then you've got the different spiral arms, the Carina arm, the Crux arm, and so on. And in the center is the galactic bulge. And this is approximately the position of the Sun. So I'll come to that again. So quantitatively, again, this is the near edge-on view of the galaxy. So you see that the size of the galaxy from end to end, the end is of course not precise. You gradually merge into the intergalactic medium. So it's about 30 kiloparsec. As you know, one parsec is about 3 light years. So you can say that from edge to edge, the diameter of the galaxy is about 100,000 light years. And the Sun is situated at a distance of 8 kiloparsec, 24,000 light years from the center. So it's quite far from the center, but nevertheless, much of the galaxy is beyond the Sun, right? And then now we'll see what the thickness of the disk of the galaxy. The disk is actually quite thin here, as you see. This is a sketch from a very nice book by Spark and Gallagher on galaxies in the universe. And then you can see the disk of the galaxy. You can see the central bulge, and then you can see that there's this dashed lines here, which actually show what is known as a thick disk. So what do you mean by the thin disk, and what do you mean by the thick disk? So, and what does the disk consist of? The disk actually consists of a flattened system of stars, right? So the idea is that most of the stars in the galaxy, many of the stars in the galaxy are actually in the form of a disk. And then a star which is there at a given distance will be gravitationally attracted by all the stars which are closer to the center. And therefore, in order to not fall into the center, the star has to go round and round and round. For example, the Sun is going around the center of the galaxy, just like the Earth is going around the Sun. The Sun is going around the center of the galaxy, and the orbital period of the Sun is about 250 billion light years. So that is about a quarter billion of light years. So for an age of about 10 billion for our galaxy, then you're really talking about the sun has gone 40 or 50 times around the center of the galaxy. So it takes a very long time to do so. So you have got as I told you, the disk consists of spiral arm-like structures, there's gas and dust. There's a lot of star formation going on in the disk. That is because when gas is present, star formation always takes place, and the disk is supported by rotation. And about 95% of the stars are in a thin disk. And as I told you, the thin disk with a scale height. When you go to the approximate thickness of the disk, you can say it's about 300 parsec. That's about 1,000 light years. And the other 5% of the stars are in a thick disk with 1,000 parsec. So just compare this 300 parsec with the 30 kiloparsec, which is the size of the galaxy. So you see that it's about the disk is just a small, very small. The thickness of the disk is a very small fraction of the diameter of the galaxy, right? And what's the stellar mass of the disk? It's about 60 to 10 to the 10 times the mass of the sun. So the bulge which is present in the center. So typically people used to say that a bulge consists of old stars. It just happens that the bulge doesn't have much gas. And when gas is not present, you cannot form new stars. The old stars which are present will be of the old stars which are present, the stars which are created in the past, the ones which are more massive evolve fast and they are dead, and so therefore you only have low mass stars. And the low mass stars tend to be redder in color, and therefore you can say that a classical bulge, it generally is composed of the older stars is redder in color, not much action going on there. But first of all, there can be hot gas in the bulge, number one. Number two, what happens is that these bulge-like structures are not all the same. In our galaxy, it is mainly what is called a classical bulge. But in other galaxies, the bulge can be what is called a pseudo-bulge. Okay, meaning that it looks like a bulge, feels like a bulge, but when you actually take a detailed look at it, so you'll find a lot of dust there. You'll also find young stars, and then you find several differences from the even dynamical differences from a classical bulge. It is believed that these pseudo bulges are continuously fed from outside. They could have been formed in interactions of galaxies. They could also be, there can be a bar-like structure in the galaxy with channels, gas, and stars cater to move toward the center. And then so the bulge, the pseudo bulges are much more dynamic. The bulge of a galaxy has a mass of about 2 into 10 to the 10 solar masses, and it has got a luminosity about 5 billion times the mass of the sun. So here you will see that the mass of the disk is 6 into 10 to the 10 solar masses. So the disk is more massive and it is brighter. Right? Now, if this is our galaxy, then it is surrounded by a very large halo. The halo is more or less spherical in shape. It consists of metal poor, that means old globular clusters and field stars. The stars generally there have a very high proper motion. What do you mean by proper motion of a star? So you see that, as I told you, that the stars are generally going around the center of the galaxy, but in addition to that, they'll be fluctuating, they'll be doing random motion. And when you actually measure the speeds of stars within the disk, you find some anomalous stars. For example, there's a star which is called Barnard star, which has been known for more than a century now. And it is moving extremely fast. And so if it is moving that fast, then it should be able to move out of the disk. And there are indeed stars in the halo which are all moving really fast. Some of them, of course, are passing through the disk at the present time, but there are many more stars. And then the mass of the halo is about 10 to the 9 times the mass of the sun. Then in addition, now this is a halo which actually consists of stars and globular clusters that we can see. But there's also a dark matter halo. And in fact, it's possible that the dark matter is the dominant part of the galaxy. So 90% of the total mass of the galaxy. So what we are seeing, and the mass that I am mentioning, is what is called the mass of the visible matter. And the visible matter is made up of stars and globular clusters. But apart from the visible matter, there's a big halo of dark matter. And we really don't know what the dark matter is made up of. I'm not going to go into that today. But it constitutes about 90% of the mass of the galaxy. All right, and you see that I've been talking about galaxies for a very long time, and once when I was preparing a talk for a galaxies, I suddenly realized a totally new discovery had been made. That was in October 2010. So these were there's a satellite called Fermi, and it observes in gamma rays. And during these observations, they spotted these two very large bubbles around the galaxy, not around the, coming out of the galaxy, which are actually emitting gamma rays. Okay, so here is a pictorial representation of it. Looks very nice, but you're not going to see it in the optical like this. Okay, so these are gamma ray emissions. So there are many, many different aspects of the galaxy that we still are not familiar with. Now, sometimes we learn about our galaxy by observing other galaxies in the universe. But then there could be faint structures in the other galaxies which we cannot see because the galaxies are so far away. So we really have to keep looking into our own backyard. So when you build large telescopes, then what happens is that we always feel that we are going to make fantastic discoveries, wonderful discoveries, very far from where we are, up toward the edge of the universe. The edge of the universe also coincides with the early epochs of the universe. But on the other hand, right in our backyard, there are so many things. So when you build a big telescope, a fair amount of time is given, not for observing very distant parts of the universe, very early parts of the universe, but our own planetary system. Because we still really don't know so much about the planetary system. There are so many bodies, what happens, the Oort cloud, and massive objects, minor planets, and so forth. And so there's a great deal of things to be discovered, both in our own planetary system as well as in our own galaxy. Okay, so now a quick review of the content of the Milky Way galaxy. I have already mentioned to you as I move along what the content is like, but again, let's take a view. The most important content of the galaxy is, of course, the stars, and which is why the galaxy takes its shape and size, and stars are the most important. And the star which is the most important to us, of course, fully responsible for our existence, is the sun, which is a completely ordinary average star. Its mass is 2 into 10 to the 33 grams, so you use the unit of solar mass. And then it has got a radius of 700,000 kilometers, which is neither small nor big by the size of stars. The yellow color tells you that the temperature must be about 6,000 Kelvin on the surface. But as you go inside, the temperature becomes much, much larger. And it is about 15 million Kelvin down the center, and which is what allows hydrogen fusion to take place, and therefore for energy to be produced, and therefore for life like our own human race to exist. Right, but when you look at the kind of the variety of there's a very large variety of stars. So on the less massive side, you've got the lower the mass of a star, the redder the color will be, because the lower is the temperature, and the least massive stars you can have are about 0.1 solar masses, and that is because the central temperature is directly proportional to the mass of the star. And when the mass goes below about 0.08 solar masses, the temperature becomes so low that hydrogen cannot fuse to helium. Right, so it cannot be a star. Then first of all, it can be different kinds of objects, and then you can get planets and so on. But not a star. A star is by definition an object in which energy is being produced, copious amounts of energy are being produced because of hydrogen fusion. Right, so then as you go toward the more massive stars, the temperature First of all, they become luminous because the luminosity is proportional to the fourth or even the fifth power of the mass of the star. The temperature is directly proportional, the surface temperature is directly proportional, the central temperature is directly proportional to the mass of the star. So you can have stars as big as about 150 solar masses, and these are what are known as blue-white supergiants. So these are very, very large stars compared to the sun. They're far more massive. Now you can't really have stars which are much more massive than this. Now that is because of the simple reason that when as the stars become more massive, they become more, the temperature increases and the amount of energy that they emit increases. So the radiation density and therefore the pressure of the radiation increases. And when the star exceeds this one, then the luminosity of the star exceeds the value which is known as the Eddington limit, so that then the pressure of the radiation simply blows off the star. Right? So therefore, on the lower side, you have got a limit which is set by the lower temperature. And on the higher side, you have got a limit which is set by because of the Eddington, which is the Eddington limit. Now the point is that this limit is absolutely fundamental. It follows from basic physics, and you cannot contravene this limit. Whereas, so below the sun, below a star, you've got a brown dwarf, and below that, you've got giant planets like Jupiter and so forth. On the other hand, the Eddington limit depends upon certain highly simplifying assumptions, like complete spherical symmetry. And those assumptions could be violated, and then you could have more massive stars. Very long ago, Hoyle and Fowler, for example, talked about stars with a mass of 1 billion solar masses. And those kind of stars have not been discovered. Okay, then, but the really large stars are what are known as red giants. Now, these are very old stars, and these evolved from stars of mass less than about 5 solar masses. And as you all know, I'm sure, as the nuclear fuel is exhausted, the central region collapses and the outer region becomes larger and larger and larger. And then as it becomes larger, it becomes cooler and therefore it becomes red. And then it becomes then what's known as a red giant. So what are the sizes of these stars? Here you have got the solar radius as a unit. And then these are 0.1 to 10 solar radii is a general radius of the star. But when you get a white dwarf, for example, after the collapse it happens, okay, then the size of a white dwarf is several thousand kilometers and is comparable to the size of the Earth. But this is not technically a star. Right, so here you can see, for example, a red supergiant could have a radius with about 1,000 times the solar radius, and so which is larger than the orbit of the Earth, which is also the orbit of Mars, and comparable to the orbit of Jupiter. Okay, which means that as our sun starts expanding at the end of its lifetime and becomes a red giant, and then it will swallow nearly the whole of the solar up to Jupiter. Okay, so that is our end is foretold, and there is absolutely nothing which can prevent that end. So, at least to the astronomer, the galaxy can be a beautiful place out in the galaxy. If you actually go there, it will not look so beautiful at all. Okay, so this image looks very beautiful, but if I keep zooming into it, then eventually you will get the pixelization. So here you are not talking about pixel. The pixelization here would be really, it is a very, very thin gas. So if you go there, you will not be able to see much. You will probably die because of the high temperature. But then astronomers use the telescopes and beautiful cameras to take this using different filters, and you get these beautiful nebulae. Now this one is what's called a Swan nebula or Omega nebula. And then, so it is about 5,000 to 6,000 light years away and 15 light years in diameter. And what gives it this beautiful appearance is that there's an embedded open cluster of 35 stars inside. These stars are young. They are emitting emitting energetic photons which ionizes the gas, and therefore the gas emits all these beautiful colors. Now, another structure in the galaxy. So this is called a Bok globule. So you see that here, all the individual stars is a very pretty picture, and suddenly you find this great void there. There's nothing there. Okay, so people have actually believed in the 19th century, for example, or even beginning of 20th century, that there are no stars there. But that would be very puzzling, because if you say that there are no stars, it means it's like a hole. That is not enough for it to be a hole. Okay, but because it is just 125 parsec away, the galaxy extends much more. So it will have to be a tunnel. And then the tunnel will have to be exactly facing us and so forth. So therefore, how do you get a hole? Are there really no stars there? The point is that when you are in doubt, you observe. You have to think of a good observation. And the observation in this case is to observe the same object through infrared, near infrared cameras. Because what happens is that the gas, the ability, the extinction of a gas goes as 1 upon, in a simple Rayleigh model, goes as 1 upon lambda to the 4. So the higher the wavelength, the less will be the extinction. And then, so if you take it and you can really see the stars there. So there are stars there. The radiation coming from the stars in the optical band of the spectrum is completely obscured. It is absorbed. So what is absorbing it? It only means that there's a cloud, a dark cloud between us and this particular part of the sky. And therefore you don't see the stars which are behind you. Now this is what's called a planetary nebula. And so when I told you that a star can expand to form a red giant, it can again collapse and you go to the next phase of nuclear burning. But when it's all over, when the fuel is completely over, and then the outer thing can explode into this kind of a structure which is known as a ring nebula. This of course happens if the mass of the star is not too large, and that is what is going to happen to our sun. It will explode like this into a ring, and then people living far away will get this beautiful picture, but we'll be dead and gone. Okay, and what you will get at the center is a white dwarf. But if the stars become very massive, okay, then when they explode finally at the end of their lifetime, then you get this kind of a supernova. This, of course, is a Crab supernova, probably one of the most famous astronomical pictures. And then at the center of the Crab nebula is a pulsar. Okay, so but if the mass of the exploding star were higher, then you would have got a black hole. Right? And then what you see here is what is a supernova remnant. So you have got at the center a pulsar, and the pulsar can have these energetic beams coming out of it. And so it is a rotating neutron star. Right? So therefore you have about 10 to the maybe 100 million of these kinds of neutron stars and black holes in the galaxy. Right? So this is the last thing I'm going to show you about the gas star cycle. So you can start at any point in the star. So there are the molecular clouds, meaning they contain molecules in addition to everything else. The molecules are responsible for the absorption. An atom can't absorb because the energy needed is very large. Molecules can be excited by small photons of much lower energy. So such a molecular cloud collapses, and if its mass is large enough, it forms a star. And then because the temperature goes up sufficiently for the nuclear burning to take place, okay, and then you form heavy elements because of the burning, and then it can explode, as I told you in many cases, as a supernova. And when supernova that leaves a hot bubble where the gas is completely in the form of atomic hydrogen clouds and which seeded with other heavier elements, these cool, so they'll form molecules, and you are back to square one here. Right? So therefore you go on, stars explode and then you form new stars. But what will be the difference? The first stars to be formed had only hydrogen and helium, and because that is what are called the primordial elements. But as you have more and more of these cycles, heavier and heavier elements are generated up to iron, and in supernova explosions you get the elements beyond iron. So the interstellar medium where you have got these atomic clouds and molecular clouds, they are now enriched with heavy elements, and therefore the newer stars which are being formed now contain a larger proportion, larger fraction of heavier elements than the first generation of stars. Right? All right, and then this is what is called a globular cluster, and these are very massive objects. They're beautiful. They're spherically symmetric. They can contain about up to 1 million stars, and the density of stars is extremely large at the center. These are very very old objects, and it was thought that these old objects were quite lifeless, but it turns out that they are very dynamic, and they have tens of pulsars and X-ray binaries in them, and that's a very very interesting story. So I now go to the galactic center. Right, so these are and Andrea Ghez. So she works in the United States. He works in in Germany, and of course they work with large groups of people, and they carried out the wonderful observations which I'll be reporting to you today. Okay, and they were awarded together. They were together awarded half the 2020 Nobel Prize in Physics for the discovery of a supermassive compact object at the center of our galaxy. And the other half of the thing, of course, went to Roger Penrose. And if Hawking were alive, he would also have shared it. But so Dr. Penrose was awarded half the 2020 Nobel Prize in Physics for the discovery that black hole formation is a robust prediction of general theory of relativity. And these are all incredibly interesting stories for another time. So we come back to the Milky Way galaxy, 100,000 light years from end to end, and what we are interested is in the central part of the galaxy. So what we want to do is to try to go to the center and try to see individual stars there and then examine their motion. Now how is that possible? So first of all, there are problems there because this is 8 kiloparsec away from us. That's the stars will be very, very faint individually. Second, as I explained to you, the brown patches that you see are patches of dust. These are absorbing the light from the stars, and then and so therefore the stars become further dimmed. You know that they get the extinction is as much as 20 magnitudes. Okay, which means that it's about 100 million times compared to the extinction compared to light we get from stars which are close to us. So then how do we do it? First of all, use very large telescopes. So they use VLT, this is a very large telescope in South America and Chile, or the Keck telescope, which is a 10-meter telescope. The VLT is 8-meter telescopes. Right? And then second, I mentioned several times in my talk that you use near infrared cameras, okay, which have not been around for as long as optical cameras have been around, and there the extinction is the least. Okay, so then what you want to do is that you want to increase the resolution because the stars will all be packed together. And so how do you increase the resolution? So then you use what is known as adaptive optics, for example. Okay, or use use high resolution imaging observations and integral field spectroscopy to obtain the spectra of a large number of stars together. So what all this means is that, I would like to explain this to you in detail at some other time, but these are incredibly high technology observations. But this kind of technology has been available over the last 30 years or so, but it has been constantly improving. And which is why, as I go through my remaining slides, you will find that there's constant improvement in the results. So the better your observing capabilities, the better your results will be. So this is a radio image. It's not an optical image at 90 centimeters. It's pretty high wavelength for radio astronomers of the center of our galaxy. And right down the center, you've got a region called Sagittarius A, because the center of the galaxy lies in the constellation of Sagittarius, and this is Sagittarius A. And then in 1974, Balick and Brown discovered a component of it which they call Sagittarius A star. Okay, and this Sagittarius A star is extremely compact, it is very small size, and it is simply not moving according to the measurements made at that time. It didn't move at all. So it must be pretty massive. And so it was agreed that it has been agreed by astronomers that this object is at the very center of the galaxy. So you can examine the center of the galaxy in different ways. And so here you see an X-ray image of the center of the galaxy. And here's a blown up thing which is around Sagittarius A star. And then you'll see that, oh my God, sorry, something went wrong. Do you see my screen?
Yes, sir, we can see.
Okay. There's a problem with my own thing here, but no problem for you. Alright, so there's a central 10 light years, and these observations are by the Chandra X-ray Observatory. So you see that from 100,000 light years, we have gone to the central 10 light years. So now this is an HKL composite. What is HKL? You know what is BVR, for example. These are filters that one uses in the optical. HKR filters that one uses in the filters one uses in the near infrared. So when I use a large camera, large telescope, adaptive optics, speckle, and near IR, right? And what are we seeing here? We see this region here. What is the size? You see this bar on the lower left-hand corner has got a size of 6 light months. So this is the thing here you're seeing. Given the 100,000 light years extent, so we already are from 100,000 light years, we are in half a light year. It's a very tiny part of the galaxy. And then you further zoom, and then you see here in Sagittarius A star, and you're clearly seeing individual stars around it. So what the two groups that I mentioned did was that they actually looked at these individual stars here, and then they followed they made these measurements year after year after year. Meaning that they started, I believe, in 1993. So this is in 1995, 1996, 1999, and 2000. Okay, and then you look at this particular star, which is called S2, and this is the one which is going to be of interest to us. And you see that the position of S2 is changing relative to S1 here, relative to the background. So the question is, can I do this for a number of years and follow the motion of S2? The difficulty, of course, is in the fact that all the stars are moving. So S2 is no doubt moving relative to the background, but the stars in the background also are moving. So which means that you have no fixed frame of reference over which you can define the motion of the star S2 from as the time progresses. And therefore, it becomes, you have to define the frame of reference, and for that, a certain number of standard stars here are used, and also there are stars which produce maser emission at radio frequency wavelengths, which can be observed at what is known as VLBI, that is very long baseline interferometry, which gives you the positions of objects within 1 milliarcsecond. And all those techniques have to be used to define a fixed frame of reference. It's incredibly difficult, right? And so after having done that, so you see that they have got several, this is an old paper, 2003, 19 years ago. And then you see that the arrows here indicate the measured velocities of these objects. And then this result, which was published by Shodel et al. In Nature in 2003, so you see that the star S2, which I mentioned, and here it appears to be swallow in the center, but this is the motion of S2 around the center. You see that this is 1992, 94, 99, 2002. It has been followed for a period of 10 years, right? And then what is the shape of the orbit? You see, it's very beautifully an ellipse, right? So you can imagine that this is very similar to what Kepler must have felt long time ago, 400 years ago. And when you looked at the orbit of Mars, and then he realized that the orbit of Mars around the Sun is elliptical in shape. Right, so you see that here we have established that the orbit of S2 is elliptical in shape. But what we have something which Kepler did. So Kepler used is the study of the orbital study of the planet to give his laws of planetary motion. But since Newton had not yet given the theory of gravitation, he was yet to be born. Kepler couldn't measure the mass of the gravitating object which maintained this elliptical orbit. He could only say that the attracting object is at one focus of the ellipse. The Sun was one focus of the ellipse of the elliptical orbit of Mars. So here similarly, Sagittarius A star is at one focus of it. This is a very elongated object. And here S2 is approaching Sagittarius A star very closely. And the peristron distance is only 78 light hours. Right? So which is 0.6 MPC. MPC typically for astronomer means megaparsec, but here it is milliparsec. Okay, and then you can say that the central mass is 3.7 million times the mass of the Sun. So this is a stupendous discovery that there is such a massive object lying at the center of the at one focus, and which coincides with the center of the galaxy. Right, so where do we go from here? First of all, you need to improve the measurements. Okay, then you have to say what is the nature of this object. So the improving the thing of the, you see that the orbital period of this object S2 is 15.7 years. So which means that you are actually seeing a star going around the center of the galaxy once every 15.7 years, which is very staggering given the size of the object and the fact that the Sun takes 250 billion years actually to go around the center once. This star takes only 15.7 years to go around the center. So you have to keep observing the star over the subsequent years to do it. And there are all kinds of exciting things which happen along the way, which I will not go into. But this is a thing which is taken much later. So again, which shows you how beautifully the positions are determined. And then in 2009, we actually see this particular ellipse, which is now complete. Okay, because then we have observed the S2 for more than 15.7 years. And then there are two surprises here. One is that the object of the center, that is extended now, which means that the object is moving, and which seem to be consistent with this part here. You'll see actually the orbits are not overlapping here. So it is not a fully complete ellipse. And so if the object at the center were indeed fluctuating, doing the small fluctuations in the position, then that would lead to an incomplete orbit like this. And you can show this very easily from Newtonian dynamics. And so now here, and then one fallout of this is that we know accurately the distance of the Sun from the center, which is 8.33 parsec. Right, and here you see that the two different groups who got the Nobel Prize, and so you see that the red ones are measurements by one group, the blue ones are measurements by the other group, and you see that the measurements comfortably overlap each other. Okay, so which means that the measurements are correct. Now, I have got about 4 minutes left, and I can see I come to the end of my talk, but I want to take you in a completely different direction. What are the beautiful conclusions which can be drawn? When Einstein gave his general theory of relativity, he immediately made 3 predictions. One is that there is a gravitational redshift. The other is that there will be bending of light, and the third is the precession of the perihelion of Mercury. So, what does the precession of perihelion of Mercury means? That if Mercury were actually going around the Sun in an elliptical orbit, and if it were the only planet, then you can, from Newtonian dynamics, you can show that the orbit would be perfectly an ellipse. Whereas, as it happens, there are the other planets to go by, different bodies. The Sun has got an oblateness. All of this prevent the orbit from being closed. Right? So which means that as Mercury goes around it, the whole orbit rotates. So which would mean that the point at which it is closest to the sun, which is known as the perihelion, actually moves in the sky. And that is called the precession of the perihelion of Mercury. And the thing which has been observed, and this was in the 19th century, second half of the 19th century, very accurate measurements show that the precession of the perihelion of Mercury is 575 arc seconds per century. That is very small. This is less than 1 arc minute. And here you are talking about per century. And so 1 arc second is 1 upon 3600 of a degree. And then now 532 arc seconds per century can be accounted for by the movement of the by the effect of all the other planets and the oblateness of the sun and other effects. And so the remaining 43 arc seconds was called anomalous. It cannot be explained within Newtonian dynamics. And then general theory of relativity, without introducing any extra constant, can exactly explain this, and which is considered to be a great triumph of the theory. So this is very small. But what are the other general relativity settings? There's something called a binary pulsar, which consists of two neutron stars going around each other in a very close orbit, and one of them is a pulsar. Very accurate measurements were made on those in 1970, ending in 1974, and then so there it was found that there is a precision of 4.3 degrees per year. That is because the orbit is very small, and then because of the smallness of the orbit, the precision is much larger because the general relativistic effect is much larger. And then, as people who discovered this pulsar, Hulse and Taylor got the Nobel Prize for physics. So now I jump forward and come to an observation which was reported in 2020 on S2, on the motion of S2. And you see that here are the cameras, the measurements which are used in the past up to 2000. And here are the measurements used in 2020. And what you find is that the RMS uncertainty in the measurement has gone here from about 10 milliarc seconds, okay, that is the RMS uncertainty, to a fraction of a milliarc second. So this is 1 milliarc second, and then 0.1 milliarc second, and so a fraction of a milliarc second. So which means that very accurate observations are possible. And then using those, this is the measurements which reported in 2020, and what it shows is that the object at the center is stationary, it is not moving, which is exactly what is expected of a very supermassive object. And then this orbit here is not closing because of what? The object has not closed because of the precession in the perihelion of S2. Absolutely amazing. Right? So we are seeing a general relativistic effect here. Here, in fact, you see the orbit is actually closed. And why it is closed is because in making the fit, the precession in the perihelion has been taken into account. And that is 12.1 arc minute per orbit, which is 12.1 arc minute in 15.7 years. And this is my last slide. So this is the artist's impression of S2, which is going around the supermassive black hole. And then when it at the closest distance in orbit, the whole precession takes place. Okay, so you see the precessed orbits here. So I'll stop now with just one remark. Everything that I've said and all the observations and the measurements have only established that there is a supermassive object at the center. We have not established that it's a black hole, but there are many, many lines of evidence which point to the fact that the object is so compact that nothing that we know in the physics of the present can have a non-collapsed object. So it is extremely likely that it is actually a fully collapsed black hole. Thank you very much.
Thank you very much, Professor Kembhavi, for your very interesting talk. Now the session is open for questions. So I request the audience either to unmute themselves and speak their questions, or they can also use the chat box. So there is a question presently in the chat box from Unmun Devi. So she's asking, it's a naive question. A few rounds of stellar evolution usually increases the metal content. I was wondering why the old globular clusters are metal poor.
Oh, see, the age of our galaxy, is about 13 billion light years, and a little bit less than that. And the globular clusters are probably older than the galaxy, which means that they have been around for a very, very long time. And the stars are all coeval, meaning that they were all formed more or less at the same time. So when the collapse took place and the globular cluster was formed, the stars the stars actually they are different masses, but the more massive star just went off very rapidly, and all that you're seeing now is the low mass stars. But please understand that the globular clusters formed very long time ago, at which time there was no enrichment of the interstellar medium, and no new stars have been formed, and therefore they are metal poor.
Okay, so are there any more questions? Okay, so let me ask one question. So, Professor Kembabi, as you mentioned that the most massive stars are the blue giants, whose masses are around 150 solar masses. So, so to have stars more massive than that, I mean, other than the fact that they may not be stable because the radiation pressure may blow them out, apart from this fact, does any other principle hold the formation of stars more massive than the blue giant stars?
No, not really. I mean, I don't think that there is any principle like that which prevents the formation of very massive stars. Okay, so for example, there are what we call the population 3 stars, which are really, really primordial stars, and they were pretty massive. But the Eddington limit, you see, so what the Eddington limit, uh, you see, the calculation of the Eddington limit depends upon the assumption of complete spherical symmetry and a couple of other simplifying assumptions. So when these do not obtain, you can have geometries which are not completely spherical symmetric and keep adding matter to the stars, and then uh, they can exceed the Eddington luminosity. So it is not an absolute limit.
Okay.
And as I said, Hoyle and Fowler had already said that there will be very massive stars, but those have not been discovered.
Thank you, Professor Kembavi, for your answer. So, if there are no more questions from the audience, then I thank Professor Kembavi for his very wonderful talk. And now we move on to
Yeah,
the
I will stop sharing one moment, please.
yes, yes. Yes, thank
Yeah.
you.
Okay.
Now we move on to the next talk of the session, which will be delivered by Dr. Indu Kalpo Dihinia from IIT Indore. And the title of his talk is Understanding the Properties of Accretion Flow Around Black Holes with GRMHD Simulations. So this is also a 45 minutes talk, and the final 5 or 7 minutes will devote for the questions. So I request Indu Kalpadihinia to present his lecture.
Thanks, Gopda. So I will share my screen now.
Yes.
Please let me know when you see it. Hope you can see it.
Yeah, it's coming. Yeah, it's visible. Your screen is visible.
Okay. So first of all, hello everyone, and thanks team NEMA for giving me this opportunity. Also the organizing committee of NEMA, congratulate them for organizing this meeting. And Okay. And first of all, I would like to tell that Rajiv Gandhi University is very close to my home. It's around 3 hours of travel by some car or something. Initially, I thought I will go for a vacation and enjoy Bihu, then I will enjoy a conference and come back. Unfortunately, now we are doing it virtually. Anyway, let's focus on the scientific part now. So already Professor Kembavi has given a very elaborate discussion on our galaxy and the supermassive black hole at the center. So here I will be talking about he also pointed out about the implication of Einstein theory of gravity and this bending of light and everything. So I will try to explain some of those parts a little bit in my talk. And so here are my list of collaborators. With the increase of state-of-art astrophysical observations facilities like Event Horizon Telescope, LOFAR, or next generation Event Horizon Telescope is also coming up, then Meerkat, and also the gravity collaboration as mentioned by Professor Kembavi. Those all are coming, and we are now abundant. We have abundance of stunning observations, and we will have more. So in order to understand these observations and abstract physics out of it required extensive numerical modelings. In my talks, I will try to give a glimpse of some of our recent findings using and how to way forward to understand these observations using numerical modeling. So my talk will mostly focus on the physics related to astrophysical jets. Astrophysical jets are very common in systems hosted by accretion disks, like these hosted by accretion disks, and sometimes it may not have accretion disks, then also it can have jet. Here I am showing in this figure some images of jet, images of M87, and in different length scale. You can see from different our telescope, and here you can see its structure of the jet. And finally, thanks to the Event Horizon collaboration that we have, it's very the region very close to the black hole and its image, and it's extremely interesting and beautiful. So now, and of course, as I said, the jet are like collimated beam of matter coming out from certain central object, and it has a relativistic speed, and its speed depends on the mass central object that is hosting the jet. So indeed, right now, there is still huge discrepancies between theoretical prediction and observational finding. Particularly, theoretical understanding of many aspects we do not know yet, or some are still elusive, or maybe some are still not studied well. For example, how jets or wind launch from black hole or from accretion disks, or how they collimate, how they accelerate to a speed of light, and how they become how they take such a beautiful structure. Those things we need to study, and maybe at the end we may test the theories of gravity also from the observations from these recent observational techniques. So astrophysical jets are often studied in three forms, in different length scales. First, the launching region, that is very close to the, if there is a black hole, let's say, as Professor Kembavi also said, that there is a disk around the supermassive black hole. Of course, the Sagittarius A star is not a very active black hole, but if there is an active black hole like M87, then those kind of galaxy may have a very large scale astrophysical jets, and they have very small launching region close to the black hole. Then we have the propagation region, then we have the termination region. So these three different regions people study differently, but comparatively to the propagation and termination region, the launching is much more complicated, as it involves very sophisticated physics, because close to the black hole we need to consider the GR effect and everything. So I think probably I will explain them in my upcoming slides. So, and before going to the detail of jet launching, I should take some time to explain accretion. Because most of the jetted system hosts accretion disks, and at least for the black hole system, the accretion disk is must necessary to have astrophysical as such jet. The story of accretion in brief is as follows: like gas with angular momentum rotate around a black hole, and it create spirally it rotate and it create a disk-shaped geometry known as accretion disks. And accretion disks matter loses angular momentum due to some kind of viscosity or magnetic stress, and fall onto the black hole, and this is called accretion process. And during this process, the potential energy of matter or gas converted into thermal energy due to the large gravitational compression, and it emit with very high radiative efficiency. And that is why all energetic processes in the universe are somehow related to accretion or some kind of accretion physics. So it is very important to study accretion in detail before studying astrophysical Z. So, what is the process? How we understand or how we can study this kind of system, accretion or relativistic Z? So, or maybe how we observe it, how we can observe a black hole. For that, two steps we need to follow. First, general relativistic magnetohydrodynamics we need to do. That means there is a black hole, there is a gas surrounding it. We have to follow the plasma along with the magnetic field line around the black hole and get the realistic time-dependent turbulent behavior of the flow. Next, let's say from the gas, there will be lots of radiation will be coming up, and because of the strong gravity, we have to consider the geodesic of those photons. So we have to do general relativistic ray tracing. So we have to follow the photon from the accretion flow and integrate to a screen which is at the infinity, or like at our Earth, like the telescope we have in the on the Earth, and then integrate using the radiative transfer equation, take account all the emission and absorption that is happening in the accretion flow and get the realistic picture. And with that, we can get the synthetic radiative properties of accretion flow, and finally, we can model it and understand about the object. So that is the way to conduct this kind of research. So first, first we need to solve that means GRMS equations. So we need to solve this all sets of GRMS equations. So this is of course the mass conservation, energy momentum conservation equation, and these are the Maxwell's equations. And then to solve this kind of equation, people like from like past 20 years or so, people have been developing GRMSD codes to do this kind of calculation. So there are many active codes like HARM that is developed by Gani, McKinney, Toot, and their collaborator Oliver Port, Hector Oliver, Mizuno, Rezola, and like that, Coral, Athena, and like that. There are many active codes. I adopt the code this Bhag code, and do my calculation. So using this code, we want to study the accretion ejection process or the disk-jet system containing accretion disk and relativistic jet, particularly the jet launching. So one of the jet launching mechanism is via Blandford-Jannach process. Blandford-Jannach jet launching it launches jets from very close to the black hole, and usually that region is known as Argo region or the argosphere. The argosphere region around the Car black hole, where matter co-rotates with the black hole. So that is how the Argo region is defined. So this Blandford-Jannach process is based on the generalized version of it called Penrose process, which essentially allow matter to come out from the Argo region by extracting energy from it. Let's say some projectile it disintegrates in the Argo region, then one of the fraction can have negative energy, and then other part can actually gain energy and go out from the Argo region, and it is as if the the outgoing fraction gain energy from the black hole. So this is the basic Penrose process. So let us consider a black hole threaded with magnetic field lines. During, let's say, some pair production and some that kind of disintegration process is happening around in the Argo region. Then what can happen? Let's say this electron-proton pair is created around the Argo regions, and then any one of those particle can gain energy from the black hole and follow the magnetic field and line and escape the black hole with relativistic velocity. So this process acts as if there is a potential difference between Dx and the Z, and then the charged particle is moving following this potential. So this process is very interesting to study with GRM, the simulation. So in here, what usually happens in simulation, people have seen that around this black hole, we have the magnetic field line threaded to the ergosphere of the black hole, and around the disk region, that is the equatorial plane, the magnetic field are mostly toroidal. That means they are as if they are rotating around the black hole. So this is the basic system. So let's try to see the simulation of Blandford Chennai Z in detail. In this movie, a typical 3D GRMSD simulation is shown where colloidal component of the magnetic component dominant. You can see around the disk region. Then we have magnetic field lines. They are threaded to they are like a colloidal magnetic field line threaded to this black hole or the Argo region. And then you can see the Z in the gray color. So in this left figure, what I am showing different. What I am showing is the Z radius versus the Z axial distance. So that means from here, using different VLBI, that is very large baseline interferometry observation, they calculated this Z radius versus the distance from the central black hole and plotted it. And they have seen that this Z structure is parabolic and it becomes conical after certain Bondi radius. And also they find that the Z launching radius is around 5.5 Schwarzschild radius. And so this strongly suggests the presence of this kind of, because Z launching region is so close to the black hole, so it essentially suggests that means Blandford Chennai mechanism is probably responsible. And also, you can see this is what we did some simulation using thin disks, and we have seen that in the funnel region, we have Lorentz factor of the order of 10 in the launching region, and the magnetization, that means ratio of the magnetic energy to the gas means rest mass energy is also very, very high. So we essentially see this kind of active Blandford Chennai mechanism. Also, this kind of Z can be very, very interesting with this kind of plasmoids, where some bright region you can see if we have different kind of magnetic field structure around the disk or the around the equatorial plane. So, but then again, recently, that means in 2016, there was a very interesting observation from Cygnus A by Bocardi et al. But they have found that using the similar technique they have done for M87, they found that the jet launching radius is around 227 Schwarzschild radius. And because if the jet launching radius is so huge, then Blandford Chennai mechanism cannot be responsible for that. And this suggests that the jet is anchored actually far from the black hole, or maybe at the accretion disk. It essentially suggests that the Blandford Chennai and some different mechanism, which is known as Blandford Payne mechanism, must act simultaneously in this system and get this structure of the Z. So, what happened in the Blandford Payne mechanism? In the Blandford Payne mechanism, what happened that if there is an accretion disk and magnetic field lines are threaded to the magnetic field, then what happened during the disk is rotating around the black hole with Keplerian angular momentum, let's say. Then what can happen? Some charged particle can cling to the magnetic field line, and it can gain energy from the magnetic field, and it can accelerate and go away from the disk, and that is known as Blandford-Payne mechanism. That is possible if the magnetic field lines are inclined less than 60 degrees to the accretion disk. And this is the schematic cartoon picture of the same. And this, yeah, of course, and this is also the same cartoon picture you can see. So till now, with simulation, people could not able to find this Blandford-Payne mechanism. So they usually do some simulation considering a magnetic tori around the black hole and do this kind of but of course they see disk wind that is mostly dominated by the toroidal component of the magnetic field, and it's launched due to the strong toroidal magnetic pressure. Very recently, this Kian and Variolis 2009, they have shown that there's possibility to have Blandford-Payne wind from if we do GRMS simulation with thin disks. And then finally, what we did, we considered a thin disk, very, very thin disk around the equatorial plane and set the inclination angle very low, means in the lower side. And then we have seen that this, here I have shown the Albanic Mach number plot basically. So here we see that this is at the equatorial plane, we have the very highly dense thin accretion disk. Then there is a region which is subalbanic region, then the matter becomes superalbanic as it moves far from the black hole. And that essentially suggests that as if the matter are stripped away from the accretion disk magnetically. And the ratio of the toroidal to the poloidal magnetic field strength is also close to unity. That essentially suggests that we have active Blandford-Payne mechanism, and we have shown it for first time that this kind of Blandford-Payne wheeling simulation is possible. And then here I saw a very interesting inner part of the disk where we see the formation of plasmoid. Where what happened that the magnetic field lines they can reconnect. That means they join and dissipate. They can dissipate magnetic energy and they form this kind of plasmoids. And what happened in the plasmoid? Basically, if there is some charged particle, let's say electron, it can gain energy from those magnetic field lines and accelerate, and that can give non-thermal radiation from the non-thermal radiation, and maybe in high energies like gamma rays or so. So these are the some kind of interesting thing that can be understood using GRMS simulations. Then this is what I can summarize our results using this schematic toy model. That means we have a Blandford-Genite jet around the rotation axis or around the two polar direction. Then we have a B-tor dominated. That means where the toroidal magnetic field is stronger than the poloidal magnetic field, and this is called B-tor disk wind. And where we see this kind of plasmoids, and this is very hot, and so it acts as a hot disk wind corona that can have very interesting implication in astrophysics. Then surrounding it, we have Blandford-Payne disk wind, whose launching radius is very far from the black hole. So these are the things we have found from our simulation. Then we also try to see the different implementation of corona model, like using a truncated disk model. There are several corona models are present in literature. So, of course, one is called the lamppost model, where corona is situated in a perpendicular direction to the black hole at a certain distance, and then from that people try to explain observation. Then we have this extended corona model where corona is close to the black hole and surrounding the black hole, or maybe it is like it's known as extended corona model basically. So what we thought that, okay, let's try to simulate some truncated accretion disks and see what happened, that it forms what kind of corona. Then what we did, here you can see some results from our truncated accretion disks. Here you can see we have this truncated disks, and then what we see that with temporal evolution, with time, the matter from the inner S loses angular momentum, and then it's proceeds towards the black hole, and then it do this precessing motion or the oscillatory motion with time. So this we find, and it happens because what happened when the flow proceeds towards the black hole, it squeezes the magnetic field lines, and then we have the reconnection events, and reconnection creates the magnetic field lines such that it has very strong magnetic tension force, and the accretion cannot penetrate this gravity cannot penetrate those magnetic tension force, and the accretion halt for momentarily. But when it again loses angular momentum, then it again can come inside and do this accretion process. So with that, we also found that while during oscillation, some of the flow properties they make some sharp transitions, like the velocity and the density and the pressure at certain distance. So this essentially show that some kind of shock wave is forming close to the black hole. And what we see with time, this shock location where this sharp transition happens, it goes closer to the black hole and finally disappear. But when the inner rays go far from the black hole, then and as it proceeds towards the black hole, then again this kind of shock forms. So now I think I don't have much time. So what I will quickly go now to how to see these things. Like in 1978, Lumiere first gave this kind of picture using our primordial supercomputers. Like we were very it's very primordial computer modeling. And then finally we have in 2016 we model this kind of images of black hole using ZRMSD and generative ray tracing. Then finally we have this image in 2019 from Event Horizon Telescope. So now the question is how to go from here to here, 2078 to 2019. So for that, this is the what is called. For that, we need to know how the photon moves around the black hole. So of course, everyone knows about the geodesic equation. What we do, we follow the photon using the geodesic equation, as I mentioned earlier, and then do this radiative transfer. That means how the intensity of the emitted photon changes as it moves towards us. That we need to know, and from that we can figure out how the black hole will look like from our telescopes. So currently, I am using this open source code called Raptor to do this kind of calculation, and this is I created from my simulation. That is for Sagittarius A star kind of mass. If we have, then what will be the image of the central object? So here you can see if we view from different viewing angle, then it will have this kind of right side and showing it from the different angle. And then if we do some kind of take the image and do collect the image from different time, then we see it has this kind of the image that I am showing the left image. But interestingly, when this was truncated disk, the disk was doing oscillation, then it was coming in and going out. That what happened? It saw very interesting feature in the radiations. So here I am taking the image in 1 keV energy. Then you can see that this inner rays is mostly bright, and with time the inner rays is coming inside and it is becoming brighter and brighter. But we see some radiation coming close to the black hole as well. That is because there is a post-shock region is forming there. Due to shock transition, hot matter is around that, and that is basically radiating those emissions. But in this below panel, what I am showing, when the disks go back and it goes far from the black hole, then what we see that the brightness of this outer edge also reduces, and the emission coming very close to the black hole is also very, very negligible. That means there is no that kind of soft region, or it is practically empty. So what is more is that if we take the emission spectra for these two processes, that is one is going inside the inner edge, inner edge is going inside, and other is inner edge is going outside. What we see that the peak frequency of this emission is increased as the accretion disk moves towards the black hole, and when it goes far from the black hole, the emissivity, the peak frequency drops, and the luminosity also it changes accordingly. Like when this moves closer to the black hole, the luminosity increases, and when it goes far from the black hole, the luminosity drops drastically. So, and now what is next? Now what we want to study the different microphysics that are happening in the accretion flow, like radiative cooling, or how electrons are heating up, how Coulomb interaction that is acting in the black hole can impact the flow. This right now I am trying to do this kind of calculation and use this GRRT, that means general relativity ray tracing, to understand this observation from EST or GMV, that means global millimeter very large X-ray, very large array, and then also from the next generation EST. And of course, as I want to understand the different kind of variabilities that we see that in AGNs or black hole X-ray binaries. Currently, I have working with this two temperature model in GRMSD, and here we see the different, let's say, electron is heating only due to the turbulent process, due to the magnetic turbulent process. Then if we add the Coulomb coupling, then we added the radiative cooling processes. And we have seen this process with different accretion rate and different physical mechanism, different physical region, like standard means low magnetized region and highly magnetized region. And we see that these processes really change this ratio of the temperatures drastically, and it can have very strong implication in observation. So that we want to understand in like upcoming years. Then, of course, this is the recent observation, as I said, in 2019, and finally in 2021, we have this polarized image, which basically say that the magnetic field around close to the black hole is mostly radial or vertical. That means the poloidal, and it has density of the order of 10 to the power 4 to 10 to the power 7 electron per centimeter cube, and magnetic field is of the order of 1 to 30 Gauss, and the temperature is of the electron temperature is of the order of 10 to the power 12 Kelvin also. And the magnetic field is practically important. That means it's called MAG. That means magnetically arrested disk, or the magnetic field really is required to understand this accretion flow close to the black hole. And now we would like to go. We will have much more new findings and new results. We need to study them and understand physics close to the black hole. And so, yeah. So I would like to thanks for your attention. And if there's any queries, and I am happy to answer.
Thank you very much, Dr. Dhinia, for the very interesting lecture. Now the session is open to questions. So I request the audience to either unmute themselves and put forward their questions, or they can also use the chat box. So are there any questions? Okay, in the meantime, let me put a question to Indu. So, Indu, so observationally, how much observational evidence supports the Blandford-Naik process, and how many I mean, what is the ratio? What do you feel? How many observations support the Blandford-Payne process, and how many observational evidences support the Blandford-Naik process?
Okay. Most of the observations right now, like for for many active galaxies and astrophysical, that they mostly find that the jet launching radius is very close to the black hole. So they often try to say that it's probably the Blandford-Naik mechanism, but there are a few observations right now coming out, like in recently in 2019 or 20, Bocardi et al. They have some new, means there are very few that say that the jet launching radius is very far. But thing is that when it depends on the resolution that we have for this observation, then probably we may have, if we increase the resolution, then we will have people will have much better picture. But most of the observations are this 10%, means the launching radius is close to the plane.
Okay.
Very close.
Okay, and suppose we devote simply to the hydrodynamic simulations, then what do you feel? I mean, what are the results? What is the distance of the jet launching region from the center of the black hole? So here, when I'm talking about hydrodynamic simulations, then we are not invoking the Blandford-Naik or the Blandford-Payne process. So what do hydrodynamic simulations suggest?
Okay. In that case, probably we will able to understand accretion flow around the equatorial plane. Not if we go off the equatorial plane, then usually what happens, the magnetic field contribution is much more higher. As you have seen from this, what EST observation also suggests that it's the magnetically arrested. But around the equatorial plane, if we are around the equatorial plane, then we have the density of the gas is very high. In that case, the magnetic field contribution usually is very, very small around the equatorial plane. That definitely only with hydrodynamic model we can study. And when, let's say, how the matter go from this equatorial plane to off equatorial plane, that can have several things, right? If not magnetic field, then the thermal pressure can also push the matter to the off equatorial plane. But it can take some kind of form of some kind of wind. But how to take them, because they will have very small velocity, particle velocity. But what that we see, it has velocity like of the order of light. And so we need to accelerate those velocities to that kind of velocity. So at the launching region also so if there is magnetic field, then only we can accelerate those velocities to that kind of very high relativistic velocity.
I see. Thank you for your answers. So if there are no more questions from the audience, then I thank Dr. Dihinya for his very nice and informative talk. So thank you very much, Indu. And I now hand over the session to Dr. Sanjeev. So this particular session ends now. Yeah.
Yeah. Thank you very much, Dr. Sakars, for taking the session here. This. So. I think I'm sorry. So in this morning session, we have no other speaker. So we end the past sessions here. So from 2 the after lunch break, we'll be meeting here again, and we will have six number of talkers. So I request all to join by say 1:45 p.m. today. So we'll see. So by that time, thank you all for being with us again.
चलो खाएगा